Welcome, everyone, to this explainer. Today, we're going to unpack one of the absolute most fascinating and foundational concepts in all of computer science: tree data structures. Now, don't worry if that sounds a bit intimidating. If you've ever looked at a family history chart, or honestly, even just looked at a real tree outside your window, you already have the mental scaffolding to understand how computers organize massive amounts of data. We're going to use that exact organic analogy today to make some incredibly powerful computer science concepts completely intuitive. So here's our roadmap for today. We'll start with the anatomy of a tree, explore the different types of binary trees, check out binary search tree operations, figure out how we actually store these trees in memory, and wrap up by looking at trees in real life. All right, let's jump right into Section 1, the anatomy of a tree and a basic terminology. Okay, to really grasp this, I want you to visualize an upside-down family tree. A tree data structure is fundamentally a nonlinear, hierarchical data structure. Now, what does that actually mean in plain English? Well, think about a simple linear list, like a grocery list, where item B strictly follows item A. Trees aren't like that. They're dynamic. They're the elegant solution for data that naturally branches out, rather than just sitting in a straight, predictable line. Instead of a rigid sequence, you have these discrete points of data, which we call nodes, and they're connected by lines, which we call edges. It's really all about establishing a hierarchy. And every good hierarchy needs a starting point, right? Right at the very top of this upside-down structure is the root node. We actually call this position level 0. It's the ultimate starting block. Every single data path, every branch, every leaf we're going to explore today grows straight downward from this single solitary starting point. Notice how we define the relationships between these nodes using literal family terms. It makes it so easy to remember. An immediate predecessor node is a parent. That parent connects downwards to its successors, which are, you guessed it, children. And just like in a real family, if two child nodes share the exact same parent node, they're siblings. By leaning on this intuitive mental model, navigating a complex web of data points becomes just as natural as reading a genealogy chart. But hey, branches can't grow forever. Eventually, you hit the end of the line. And these are the leaf nodes. Just like the leaves on the outer edges of a giant oak tree, these are the bottommost nodes in our data structure that have absolutely zero children of their own. They mark the completion of that specific path, beautifully rounding out our upside-down botanical metaphor. So how do we actually travel from the root down to those leaves? We traverse the edges. Those are simply the connecting lines binding the nodes together. And if we want to understand how wide a tree is branching out at any given point, we look at the degree of a node. It turns out finding the degree is remarkably simple. It's literally just a head count of a node's immediate children. If a parent has 2 kids, its degree is 2. It really is that straightforward. Moving right along to Section 2, the types of binary trees, or as I like to call them, the different species. First things first, before we look at the species, we have to understand the golden rule of binary trees. Every single node has at most 2 children. That's it. The word binary strictly limits our structure here. A parent node can have 0 children, 1 child, or exactly 2 children, and we specifically designate those as a left child and a right child. It can never, ever have 3. Let's see how that one simple rule actually creates incredible structural variety. Think of a skewed tree, kind of like a single dangling vine. Every node only has 1 child going in a single direction, so it acts almost exactly like a standard linear list. Then you've got a strictly binary tree, where every node must have either 0 or exactly 2 children. No single children allowed whatsoever. A full binary tree takes it a step further, where every internal node has exactly 2 children, and the levels are as deeply filled as possible. And finally, the complete binary tree is highly, highly organized. All levels are entirely filled except maybe the very last one, and that last level is perfectly filled in from left to right. Oh, and there's also this totally fascinating variant called the expression tree. Trees aren't just filing cabinets for storing raw data, they can literally represent and solve mathematical formulas. The operators, like a plus or multiplication sign, sit as parent nodes, while the values or variables act as the leaves. The computer can traverse this tree to perfectly evaluate complex arithmetic. It's essentially math brought to life visually, which is just so cool. Okay, Section 3. Let's look at binary search tree operations, the ordered specialist. Now, if you need to find data lightning fast, you use a binary search tree, or BST for short. The secret to the binary search tree's incredible speed is its strict mathematical logic. The left child is always less than the root, and the right child is always greater than the root. Smaller numbers strictly branch to the left, larger numbers strictly branch to the right. It's a perfectly ordered system.
Let's actually visualize how this works with an active insertion scenario. Imagine we want to drop the number 50 into our tree. Step 1, we start at the top and compare 50 to our root node. Step 2, we just follow the rule. If 50 is smaller than the node we're looking at, we instantly move left. If it's larger, we instantly move right. We continuously ask smaller or larger as we travel down the branches. Step 3, the exact moment we hit an empty spot at the bottom of the path, we place our number 50 right there as a brand new leaf node. The sorting process becomes entirely visual, super logical, and incredibly fast.
That brings us to section 4, storing trees in memory. Basically, the soil they grow in. So we have this beautiful mental model of branches and leaves, but how does a computer actually plant these in its soil behind the scenes? Well, it generally uses two types of representation, static and dynamic. Static representation uses fixed arrays. It relies on strict math formulas, like finding a left child at index 2i plus 1. It's super easy to implement and index, but here's the catch. Because arrays are a fixed size, if your tree is missing branches, you end up wasting a ton of precious memory on empty space. Dynamic representation, on the other hand, uses flexible pointers. Think of these as literally little directional signs in the computer's memory saying, hey, go over here for the left child. This dynamically allocates memory only when a node is actually created. It's incredibly efficient and flexible, which is exactly why pointer-based dynamic representation is absolutely the preferred method in modern programming.
And finally, Section 5, trees in real life. The forest, so to speak. It's time to step back and look at the whole forest. Because trees are absolutely everywhere in your everyday technology. When you open up folders inside of folders on your laptop, that computer file system is a tree. When you interact with an AI, its complex choices are often mapped out using AI decision trees. From the GPS route planning in your car to the massive database indexing powering your favorite apps on your phone, all the way down to the simple drop-down menus in website navigation, tree data structures are the invisible backbone making modern computing organized and efficient. To kind of wrap this whole explainer up, we can distill our source material into one really elegant equation. A tree equals nodes plus edges plus a hierarchical relationship. Honestly, if you remember nothing else today, cement this foundational mental model into your understanding. It perfectly captures everything we've explored. We've covered a lot of ground today, journeying from a simple upside-down route to the massive forests powering artificial intelligence and global GPS networks. Hierarchical data truly is everywhere. So I want to leave you with a question to spark your curiosity. Now that you know the hidden architecture of the digital world, what will your next tree build? Thank you so much for joining me in this explainer, and definitely keep exploring.